and welcome to the Data Science Salon Play Weekly Video Series. Serverless has been widely accepted as a mechanism to deploy and run software really easily. However, the cost of running production-scale workloads on serverless can be surprisingly high. Wouldn't it be great if we could get the same benefits of running workloads on serverless without the hassle of worrying about those high costs? Well, in this video, Denver Serrao, a senior software development engineer at WP Engine, will walk you through a real-life example of how they actually use Google CloudFunctions at WP Engine to deploy a serverless data pipeline and then transition that workload using CloudRun and Kubernetes to achieve the same exact results but at a way lower cost. I hope you enjoy this video.
My name is Denver Serrao, and I'll be speaking to you today about managing serverless costs with Kubernetes. Serverless is an extremely popular tool to deploy and run workloads in the cloud. What I hope you take away from the talk today is an overview of what happens when you run a workload on serverless, some of the limitations that can occur when running serverless, and how they impact cost. And we'll walk through our journey of addressing some of these limitations and how we got more bang for our buck when running serverless. Feel free to ask any questions via the chat window, and I'll be answering them as we go along through the presentation. So now, a quick plug for the company I'm at. I work at WP Engine. We provide our customers with a platform to build effortless digital experiences using WordPress. So whether you're building a landing page for a marketing campaign or an e-commerce website for your clients or your own personal travel blog, we allow you to just focus on your business, and then we'll take care of speed, scalability, performance, and security. So to start off, what is serverless? Serverless is a pretty broad term. So just to clarify, what I'm talking about today is specifically serverless compute. The most common of which is function as a service. AWS Lambda was the first incarnation of serverless functions as we know it today. So I'll reference this from their website. As the name suggests, the idea behind serverless is that you don't need to provision any infrastructure. You just provide the code, what should trigger that code, and the serverless framework takes care of the rest. The biggest call out here is that you only pay for the time that your code is actually running. The classic example of this is using an API gateway backed by a serverless function like AWS Lambda to implement a RESTful API that does CRUD operations on a database. CRUD being create, read, update, or delete. Besides provisioning the database itself, using this pattern, you can implement a highly scalable RESTful API without deploying any web servers. Another great pattern is using a queue or a pub subtopic to trigger serverless functions. So while your applications are running, they can publish events to this queue, like SQS, for example, or a pub subtopic like SNS, Kinesis, or Google Pub Sub. And then serverless functions can get triggered from these events. The cool thing about using this pattern is that you get a lot of great functionality out of the box. You get auto scaling, automatic retries of failed events, exponential backoff, meaning you wait for longer intervals before retrying failures on the same event, and dead lettering, meaning you give up after max retries. So all this great functionality is provided to you without writing any additional code. The cloud providers saw this pattern gaining popularity and then added native integrations between serverless and other cloud services that they provide. So for example, S3 or GCS buckets can trigger serverless functions whenever a file is added, deleted, or modified in a storage bucket. DynamoDB, Firestore, and other NoSQL databases can also stream events that trigger serverless functions whenever data inside the database changes. So this virtuous cycle has led to serverless functions being widely used to deploy and run workloads. One thing to note is that because it's so easy to deploy and run, it can also be easy to run up a big serverless bill. Running production scale workloads on serverless can at times come with some sticker shock. So let's look into what's needed to set up a serverless function. As we mentioned, you provide your code and a mechanism to trigger that code. What's often left out is that you also need to provide the amount of resources that you allocate to that function. For serverless functions, this is generally the amount of memory you allocate to the function. And those resources directly correlate with the cost that you pay. So now let's assume that we have a serverless function that gets triggered by an HTTP request. So when that HTTP request triggers the function, the serverless provider will start up an instance to run the function on. Sometime after that, the code itself starts executing. And then once it's done, assuming no other requests come in, the instance will die out. So let's use this gray box to denote the time that the instance is running, and this green box for the invocation of the code. So you're only billed for the actual invocation time. So now when a second event fires after the first invocation completes, the same instance will serve that second invocation. But what happens if the second event fires while the first invocation is still running? Serverless functions have a limit that an instance will only serve one invocation at a time. And so the serverless framework sees this and then starts up another instance to serve the second event. If we receive a third event after the first invocation completes, then we see that it can be served by the first instance since it is now free. So now let's look at what happens inside the invocation itself. So let's assume that your code needs to make a call to an external API. And let's say that that API takes on average 500 milliseconds to respond. That's 500 milliseconds of execution time that you are being charged for, even though the function that is your code is doing nothing, is just waiting. If the instance could serve another invocation, it actually has the resources to do so. But because of the one invocation per instance limit, it cannot. This results in wasted resource time, and that costs you money. Now let's look at another scenario. Let's assume that your function needs to read a file from a storage bucket into memory. Now let's assume that 128 megs is what we allocate to the function, and that 95% of the time, the file is small enough that 128 megs is more than enough to read the entire file into memory. But occasionally we get a big file, and then we read that big file into memory, we exceed the 128 megs that's allocated. The serverless framework will actually see this, and it'll kill your invocation. So because of this, we always have to over-allocate resources to handle peak load, even though most of the time, we won't actually use all those resources. This over-allocation of resources translates to your serverless dollars being wasted. If you worked with serverless before, you're probably familiar with the concept of cold starts. This is where the time it takes to start up a new instance to run your code is much greater than using an already spun up instance. And this is quite often the case with spiky traffic patterns. So in this example, we get a cluster of 5 events at the beginning. And so all those 5 executions on the left are cold starts because they need a new instance to be spun up, compared to the warmed up executions on the right. So for example, if normally it takes 200 milliseconds to run your serverless function, when your function experiences a cold start, that runtime could be, say, 1 to 1.5 seconds. Your function takes longer to run, and you get charged more as well. So as we see, these 3 factors combined can be the cause of higher than expected bills. We have to allocate more resources than we need to avoid the instance getting killed. But we have to pay for invocation time while we're waiting on external dependencies. And then we also have the problem of cold starts, which can have slow execution time and can be expensive. So all of these factors really boil down to the same root cause, which is the limitation of a single invocation per instance. So the cloud providers have seen this and have an answer, which is to run containers instead of functions. AWS has a service called Fargate. Google Cloud has CloudRun. Azure has container instances. These services allow you to get all the benefits that you get from serverless functions, but allow you to run multiple invocations in a single instance. What's even greater is that you only get billed for the time that you have at least one request running. So even though in this example, these two invocations overlap, you only get charged for a little bit more than a single invocation. And this key difference allows you to make a lot more efficient use of the dollars that you're spending on serverless. So let's look back at our serverless setup and what needs to change to be able to use serverless containers. The only thing that you really need to do is to package your code into a container image. And this can normally be done using a CI/CD pipeline of your choice. And then you upload that image to a container registry. Besides that, everything else remains the same. You still get all the benefits of serverless execution, auto scaling, automatic retries, dead lettering. All those benefits that you got before still apply to serverless containers. So now let's compare these two from a cost perspective. Let's assume that I allocate 128 megs to my serverless function and it runs for 1 second. Let's also assume that 128 megs for 1 second costs $1. Now the real cost is much, much lower, but this is just for illustrative purposes. So with that, the cost per run for actually serving these 3 events comes up to $3. With serverless containers, the same instance is able to serve all these 3 events concurrently. Assuming the same cost structure, we only get billed a little bit more than $2 to serve these 3 events. So now let's take this a step further. Looking at this workload, we get a cluster of 5 events at the beginning and then 5 events a little bit later. So for now, let's just ignore the problem of cold starts. With the same assumptions as before, it'll cost us $10 to serve these events with the same $1 per invocation cost. Now let's look at serverless container option. We can serve all these 10 events with a single instance, but now let's assume that we need more resources to be able to serve all of these concurrently. Let's assume that we need double the memory, so 256 megs, to be able to serve all these events concurrently. So then my instance cost doubles from $1 to $2. But my billable time has gone down from 10 seconds to 4 in this scenario. So then my cost per invocation in this example has gone down to 80 cents. So this shows how we can get more efficient use of the serverless resources that we're paying for. But let's not forget about our problem with cold starts. So let's just assume that a warm start takes 1 second and a cold start takes 1.5 seconds. So with the same assumptions as before, our cost goes to $12.50, so $1.25 per invocation. With serverless containers in this scenario, we'd only have one cold start. The other events from that initial spike of events all get scheduled to the same instance. And so our cost goes down from $12.50 to $10.50, even taking into account all the cold starts and the increased instance costs to serve all these events concurrently. So now, while this is all good theory, let's move on to a practical example. So let me set up the problem here. At WP Engine, we host our customers' websites on servers in the cloud. We partner with a company called Cloudflare to provide an additional layer of security to our customer sites, which blocks malware, DDoS attacks, and other bad actors at the edge. And we'd like to be able to show our customers how many attacks we blocked for them. To do that, we used to have a Kubernetes service, which would pull these firewall events from Cloudflare. We would then augment the data in these events with data from our internal APIs, and then write the augmented data over to BigQuery, which is a data warehouse service that we use provided by Google Cloud. So in order to transition to a more event-based architecture, this changed to a structure where Cloudflare would push events to us as files on a storage bucket, and that would then trigger serverless functions to do what our Kubernetes service used to do. To give you an idea of the scale of the problem, every 5 minutes, we would get one or more files dropped onto the bucket, depending on how much traffic our platform was serving. These individual files would range from 300 megs all the way up to 4 gigs. And the files themselves contain data about each request, whether it was blocked at the firewall, which firewall rule led it to be blocked, and so on. And here are some numbers to show the amount of traffic that we would get on a weekly and a daily time basis. Because the files were so big, we couldn't just handle them in one go. And so we split up our workload into 2 serverless functions. One, which we called the splitter, which would take the incoming file and break it up into chunks, and then write those chunks into a temporary bucket. Those chunks getting created in the bucket would then trigger a second serverless function, which we call the BigQuery writer, that would augment the data in the chunks with data from an internal APIs, and then write that augmented data over to BigQuery. And here you can see the number of invocations per second for each of the serverless functions. On the left, the splitter would not get too many invocations. It was essentially 1 request per file that came in. However, as the splitter broke up that file into several chunks, that generated a lot of load for the BigQuery writer function. And as you can see in this example, we were consistently getting like 4 to 6 invocations per second. And here you can see the number of instances that were stood up to serve the load. And as you can see, the BigQuery writer instances would spike up to 80, and in some cases, like several hundred instances to be able to serve the workload. Furthermore, we can see that the number of instances would rarely go all the way down to 0, because it would keep getting more load added to it on a 5-minute cadence. Now let's look at the memory used by these functions. As you can see, the memory usage also would vary a lot. The BigQuery writer was relatively stable, but the splitter, on the other hand, would vary a lot, and that would depend on the size of the files that were coming in. And so we would have to over-allocate resources to avoid the function getting killed. Then we started to use CloudRun, which is Google Cloud's serverless container framework, to run this same workload. The top row shows the active instances for the serverless function compared to the instances using serverless containers on the bottom row. The splitter didn't show that much difference, but if you look at the BigQuery writer, you can see that because we are able to handle events concurrently, we can serve that workload with way fewer instances. The maximum number of concurrent requests that an instance can serve is a knob that you can tweak. And the more concurrent requests we allow, the more efficient we got from a cost perspective. When we increased that to the maximum allowed number, we were achieving savings of between 6 to 10% on a day-to-day basis, just by making this change alone. If we could allow even more concurrent requests, we could probably achieve even more savings. Because looking at the resource usage here, we would rarely go up to more than 70% utilization. Another thing we noticed is that using CloudRun, or the serverless container framework, the number of active instances now would quite often scale down to 0. That would mean that it would actually complete the backlog of work before the next batch of work would come in on that 5-minute interval. So this led us to investigate, what if we limited the maximum number of instances that the serverless container could scale up to? Could we still keep up the amount of work that was coming in? On the right, you can see the number of instances when we throttled the CloudRun to not scale up to more than 5 instances. And as you can see, we were still able to keep up the amount of work coming in. Furthermore, if you look at the resource utilization, that line is now a lot more smooth because we are a lot more tuned to the workload than we were before. So now let's look at the savings. When we went from serverless functions to serverless containers, we were getting savings of 6 to 10% on a day-to-day basis. And then when we added throttling, that increased our savings to 20%. So this demonstrates how using serverless containers is a great way to get a lot more efficient use of the resources that you're allocating to serverless workloads. But wait, there's more. With serverless containers, we're effectively running containers on cloud managed infrastructure. But what about Kubernetes? Kubernetes is the de facto container orchestration platform in the market. And if you're using a managed Kubernetes offerings, then the savings from serverless containers can be even higher. AWS allows you to run Fargate on EKS, which is AWS's managed Kubernetes service. Same for Google CloudRun on GKE and Azure Container Instances on AKS. These are all relatively new offerings, some of which are still in beta, but they offer an exciting value prop in terms of costs. So what's the difference here? The final amount that you get charged for serverless containers depends on two factors. The billable time, or the billable instance time, and this is the green box that we've been seeing in previous diagrams. And this is the major component of the cost. A smaller component of the cost is the number of invocations that you run. So now when you run serverless containers on the cloud provider's managed Kubernetes service, that first component, which is the major component of the cost, essentially goes away. It's effectively covered by the amount that you're already paying for running your Kubernetes nodes in your cluster. And so then you're just left with the number of invocations component, which is a really small part. Just for context, if you're running on GCP CloudRun, the cost for number of invocations is 40 cents per million. Another great benefit of running serverless containers on Kubernetes is that you can tune your CPU costs. Going back to our slide on setting up serverless, if you remember, we need to specify the resources that we allocate to serverless, to the serverless function or container. With serverless functions, we had to specify the memory that we wanted to allocate. With serverless containers, we can specify both the memory and the CPU that we allocate. And as you may know, cloud providers charge a lot more for CPU than they do for memory. So if you're running a workload that is not CPU intensive and you allocate one CPU to it, you're not really using it. And if you're not really using it in the case of a non-CPU intensive workload, so then those dollars are getting wasted. When you run containers on managed Kubernetes, you get a lot more fine-grained control here. And you can even assign slices of a CPU to your serverless container. With Google CloudRun, you can go all the way down to 1/10 of a CPU to be allocated. So this can help you if your workload is not CPU intensive. So these 2 points show that using a combination of serverless containers and managed Kubernetes allow you to achieve even more savings. And that's something that we're actually investigating at this time. So that covers primarily what I wanted to talk about today. In summary, I hope you leave with a better understanding of the inner workings of serverless executions and the limitation that may be costing you money, which is namely the one invocation per function instance when using serverless functions. And we've demonstrated how using serverless containers avoids that limitation and thereby helps you to get the most efficient use of your serverless dollars. So with that, I thank you all for your time, and I'll open it up to questions.
Thank you so much for watching this video by Serrao, Senior Software Development Engineer, WP Engine. Did you enjoy this video? If you did, please leave us a comment and subscribe to the channel below. If you like technical content and are into data science, machine learning, and AI, this is the channel for you. And I hope to see you next time.